Hello everyone, welcome you all at Lokesh sir, Unlimited Study Zone. So we starting today here students, mutual induction. So what is mutual induction? In last class we have seen the concept of self-induction. Okay, it is somewhat different from the mutual induction. In self-induction, you've seen that in an inductor coil, if there is changing in current, okay, by changing the voltage 1, 2, 3, 4, 5. So by this voltage regulator, you will change the voltage and accordingly the current will change. Right, beta? So the changing amount of voltage will give your changing current, and changing current will rise the changing flux that will be continuously increasing as the current is increasing. Okay, as the current is growing, now to identify, you can use a galvanometer. So as the flux is changing, by the changing of flux with the rule E is equals to d phi by dt, there is an opposite EMF, like your applied EMF is plus and minus. So there is an opposite EMF plus and minus will be rise inside the coil. And this is called self-induced EMF. Okay. This EMF is called self-induced EMF. Okay. So in the last class, we have find the value of this EMF. E equals to L di by dt. Right? This was the EMF. Now see, if it is your first coil, this is called your primary coil. Okay. And here it is a galvanometer, and this is a voltage knob. Now you keep a nearby coil, neighboring coil, just near the original coil. Okay. This is called primary coil, and this one is called secondary coil. Right. So as the flux will grow in the primary coil, then certainly some amount of flux that is produced by the primary coil will be linked with the secondary coil. Agree? Yes or no? Like if the flux is continuously growing, then it is also the flux produced by the primary coil, not total flux, some of the amount. Okay. So if the flux here is phi 1, so this flux, the associated flux with the secondary coil, you can see it using red color, this much amount. This is what? This is flux in the second coil, but because of first coil. Okay, this is phi 1. Clear or not clear? Now you tell me, the phi 1 is directly depending on the current in the primary coil. Yes or no? Because this flux is created by the primary coil. This is the created by this current I1. So the flux phi 1 is controlled by this current I1. Right? If I1 will increases, the amount of flux linked with the secondary coil also increases. If it is decreases, then it also decreases. Okay. So there is a opposite EMF, back EMF will create, that is called self-induced EMF. Okay. But here also one more EMF is developed along with the primary coil. This is called mutually induced EMF. Clear or not? So if you place a galvanometer here, the coil of galvanometer will also move. Okay, will also deflect. So this process is called mutual induction. Clear or not clear? Yeah, this is called mutual induction. Mutual means along with neighbor, along with neighbor, with the neighbor. Okay. Okay, so Nathan, today is Diwali. So like happy Diwali for you. And if your neighbor blast a bomb in his home, okay, cracker in his home, definitely you will enjoy the sound of that one. Yes or no? So such is called mutual induction. Okay. Okay. So yes, mutual inductance. So first it is mutual induction, then after it is mutual inductance. Mutual inductance is the property of two joint coils. Mutual inductance is the joint venture by the two coils. Because when the coil is alone, there is no chances to rising of word mutual. Okay. So word mutual is after coming of the second coil. So let us start the mutual inductance. What is inductance? Mutual induction. It is the property of two coils by virtue each opposes any change in the strength of current flowing through the other by developing an induced EMF. Once again, it is the property of the two coils by virtue of which each opposes any change in the strength of current flowing through other by developing induced EMF. Yes, each of the coil will oppose the change in this current. Okay, no one wants that this current is changed. Okay, so here as the current is changing, flux is also changing in the primary coil. So a will back EMF will result. Okay. Similarly, here it is also mutually induced EMF will produce. Okay. Clear or not clear? Yes. So check here the direction of this is the direction of main current. Okay. So in the opposite direction, a current will be there. Induced current. Clear or not? Yes. On okay. Now see its experimental proof. On pressing or releasing key K, whenever you press the key K, so initially the battery was disconnected, so the current was zero. Yes or no? But as you press the key, like there is a 10-volt battery, so the current will be rises. Yes or no? As the current is rises to the maximum value, till the current will rising, flux is also rising. So the changing magnetic flux is linked with this coil. So till the current is changing, okay, changing current I am given by small I. So for the changing current with respect to time, there will be a change in flux associated with the second coil, and there will be a mutually induced EMF. Obviously, if the circuit is closed, there will be a induced current also. Okay. Yes. So on pressing the key K, current P, current in P increases from 0 to the maximum value. It takes some time during the time current P in increasing, therefore magnetic flux link with the P is also increasing. And S is close by. Yes, S means secondary coil is close by, nearby. Magnetic flux associated with this also increases, and EMF is induced in S. According to Lenz law, the induced current in S would oppose the increase in current in P by flowing in a direction opposite to the cell current in P. Yes, if the main current is flowing in this direction, then the induced current will flow in the opposite direction. Clear? Okay. Second case, first you have seen when you close the key, and second you release the key. As you release the key, what will happen? Current again back from its maximum value to zero value, here minimum value, right? So current is continuously decaying in the first coil, so that will result decrease in flux. Here is also it is decrease in flux, but the both the coils do not want to change of flux, so they will support in the flowing coil, and they will have the direction like this. Clear or not clear? They do not want change, so they will support the decreasing current. So on releasing key K, current in the coil P decreases from maximum to zero value. It takes some time. During this time, current in P is decreasing. Therefore, magnetic flux link with P is decreasing and S is held close by. Magnetic flux also with S is decreases, and EMF is induced in S. According to the Lenz's law, induced EMF in S during break flows in the direction in the cell current in P so as to oppose the decrease in current. Yes, I just said if the current is decreasing, so the induced current will have same direction in the primary circuit, right? Yeah, so it will encourage. As it is decreasing, so it will encourage. And if it is increasing, it will discourage. Okay? Yes. Okay, so this this process is called mutual induction. Okay? This process is called mutual induction. Induction. And the EMF produced here across these two terminal is called mutually induced EMF. Okay? The EMF produced here is called mutually induced EMF. Right. Now we are going to learn what is mutual inductance. Yes, mutual induction is a process. It's a phenomenon. Okay, mutual induction is a phenomenon. Is the event. Just you seen here is the event. But mutual inductance is the property of two coils. Okay, property of joint coils. How can you define what is mutual inductance? Okay, so I1 is the let I is the strength of current in the one coil, and phi is the total amount of magnetic flux linked with the all turns of the neighboring coil. Yes. So I is the current in the first coil. Okay. And phi is the total amount of flux. Yes. This total amount of flux equals to phi. But in the neighboring coil, it is not compulsory that all over the flux is linkage, except there is perfect linking. Later on, we will see the perfect coupling is there. Yeah. So amount of magnetic flux linked with all the turns to the neighboring coil. Yes. And phi is the amount of magnetic flux. Yes, it is. It should be here phi 2 because primary coil flux is phi 1 or phi, then it will be phi 2. Okay. Okay. Then it is found that the flux on the secondary coil is directly proportional to current in the primary coil. Yes, obviously, because the flux depending on the source current is I1. Yes or no? So phi 2, if you eliminate, so we have seen phi is 2, 1 is directly proportional to I1. We just seen that phi 2 is just proportional to I1. So eliminate the proportionality sign. Phi 2 is equals to MI1, right? M is the constant of proportionality called coefficient of mutual induction. Yes, this is called coefficient of mutual induction or mutual inductance, right? Both are same inductance. Now see, phi 2 upon I1 is equals to M. With meaning, what is mutual inductance? Amount of flux linkage with the secondary coil per unit flow of current with respect to flow of current in the primary coil. Okay. Yes, you can define M also. If I1 equals to 1 ampere, mathematically, if I1 equals to 1 ampere, then M equals to phi 2 upon I1. I1 you have taken 1. So M becomes equals to phi 2. Yes or no? So what is M? M can be mathematically defined as the amount of flux linked with the second coil. Okay, when 1 ampere of current is flowing through the primary coil. Clear? Yes, note it. Yes. So it is the amount of flux linked with the second coil when we flowing a unit current in the primary coil. So M is a constant of proportionality and it is called coefficient of mutual induction or mutual inductance. Okay, if I1 equals to 1, then phi equals to phi 2 equals to M. So this is important definition. Thus, the mutual inductance of a two coil is equal to the amount of magnetic flux linked with the one coil. What one coil? Second coil. Okay. When unit current flows through the neighboring coil. Okay. So make it the better word. Make here secondary. Okay. With a secondary coil. When you flow a unit current in the primary coil. Okay. Got it? Yeah. Now, amount of induced EMF. Yes, we know the amount of induced EMF given by the Lenz's formula is equals to minus of d phi by dt, right? So here the mutually induced EMF is equals to what flux of change here? That is phi 2 is changing here. Clear in the second flux because we're talking about the secondary coil. Equals to minus of d by dt and the value of phi 2 equals to mi1, right? Yes, mi1. Where from where am I1? From here. Phi 2 is equals to mi1. Clear? So place the value. E equals to minus of m di1 upon dt. Very, very important formula. This is the mutually induced EMF. Okay? Yes. So E equals to minus m di1 upon dt. Now define m using this. So if you consider di1 upon dt is equals to 1 ampere per second. 1 ampere per second means the rate of change of current in the primary coil is equals to 1 ampere per second. That is current amount of current is changing by 1 ampere per second in the primary coil. Then the so if put is equals to 1, then E2 is equals to what? Minus M. Then the induced EMF is equals to coefficient of mutual induction. Got it? Yes. So unit of M is Henry. Same with the like in the self induction unit of self inductance was Henry. Same here. The SI unit of M is Henry. If di1 upon dt is equals to 1 ampere per second, then E2 is equals to minus M. So the mutual inductance of two coil is said to be 1 Henry when a current changes at a rate of 1 ampere per second in the primary coil induces EMF equal to 1 volt in the other coil. Clear? This is the definition for 1 Henry. Okay? Why? Because E equals to minus M di1 upon dt. Okay, so M equals to minus E upon di1 upon dt. Okay, Mm. Now take the amount of current per second equals to 1 ampere per second and EMF equals to 1. So this equals to 1 by 1. So M equals to how much? 1 Henry. Done. So M equals to 1 Henry. Oh, okay, sure. Nitin, give me 2 minutes. Okay, some of them I get start visiting me. Okay, so give me the 2 minutes. So mutual inductance depends on. Okay, so like yesterday we have derived derivation of self inductance that is equals to mu naught L equals to mu naught N square I A upon L. Yes or no? After some time we are going to derive the same derivation for mutual inductance. Previously L is here, but now M will be here. Okay, so in that one we say we are going to see that geometry of two coils. Okay, size of coils, their shape, number of turns, nature of material in which two coils are wounded. Yes, so on these factor mutual inductance depending distance between the two coil. Okay, so distance between the two coil. Okay, so your point is valid here. Also there, relative placement of two coils, orientation of these two coils means how closely the two coils are wounded. Like if they are wrapped over one another, then there is perfect coupling. Okay, all the flux created by first coil is linked with the second coil. Clear or not? Okay. Now, coefficient of coupling is not in our syllabus, but only formula is there. So make it one. M equals to under root L1 L2. Okay, remember this formula only. Okay. Yes. See the cases. For the figure A, coupling coefficient of coupling is maximum. For the second case, the coupling is less than in the first case. And here the coupling is minimum because only this much amount of flux will link. Yes or no? Hmm. Okay. Now, this is numerical question. Okay. We have to derive the coefficient of mutual inductance. But before that, this numerical. Important CBSE numerical. Two concentric coils C1 and C2 of radius R1 and R2, where R1 is less than R2, means smaller radius is inside, respectively, are kept coaxially. If the current is passed through C2, then find the expression for the mutual inductance between the two coils. Okay? Yes. So in case of two concentric coils, current is flows through the one coil and EMF is induced in the second coil because in second coil flux will be changed. Clear? Now I2 current is passes through the coil C2. If I2 current is passes through the C2, you know when current is passing through any coil, the field inside the magnet is circular coil is parallel. Okay, parallel to the axis, and the amount of field equals to B2 equals to mu naught N I upon 2R. So mu naught N I upon 2R. So check the values here. Mu naught here it is equals to N2, then I2, then 2R2. Clear? So this one is for B2. Now the field produced by this coil will be linked from the primary coil. Yes or no? As the primary coil is inside this C2 coil. Okay. So flux will link with this C1 coil that is inside. Flux is equals to magnetic field multiplied by area. Whose area? Area of coil 1. Whose magnetic field? Magnetic field of coil 2. Okay. And whose number of turns? Primary coil number of turns because the flux will be linked with the primary coil. Right. So phi 1 equals to N1. The B2 equals to, from the above relation, mu naught N2 I2 upon 2R2 into area of the first coil, that will be equal to pi R1 square. Yes or no? So now phi equals to, by the relation phi equals to Mi2. Clear? So relate, this is Mi2 right side of the flux from the from the second coil, or you can say final flux, and this is equal to flux. So both fluxes are equal. So relate Mi2 is equals to mu naught pi N1 N2 R1 square I2. I2 and I2 get cancelled. This is the relation for the mutual induction inductance. Clear? Okay. Derive it, beta. This is very important. Okay. Yes. So students, now we are doing the derivation for mutual inductance for the two coils, two neighboring coils. Okay, two solenoids. And after this derivation, we will establish that, like on what quantities M depends. Okay, so M will depend on which quantities. So consideration, write the consideration. There are two coils. Check there. This is S1 is the primary coil having N turns, the blue one coil. Okay, and a bigger coil that is perfectly wrapped over that. Okay, is called S2 secondary coil. Okay, if you talking about the radius, the S1 coil having a radius of R1, that is smaller. Okay, and for the this one coil, bigger coil, consider the radius is equals to R2. So area of cross section for A2 will become pi R2 square, and area of cross section for coil 1 A1 equals to pi R1 square. Got it? Consider the two solenoids S1 and S2, each of the length L. N1 and N2 are the number of turns. in the solenoid S1 and S2. Clear? So S2 is bounded closely over S1. So both the solenoids are considered to have a same area of cross section A. Why? Because I will take the common area. Yes or no? And the overlapping area is equals to the smaller area. Clear or not? So the effective area is equals to will be A. They having the same cross section area. Okay. Now I1 is the current flowing through S1. Now I am giving the current, given the current I1 from the first coil. Obviously the flux will be created and that flux will be linked with the second coil. So to identify the amount of flux, first we should know the amount of magnetic field. Yes. So the magnetic field produced at a point inside the solenoid. You know, B equals to, for a solenoid, B equals to mu naught Ni. Clear? So B equals to mu naught. What is N? Number of turns in the primary coil. N1 upon length is equals to L. Both the coil having the same length. Clear or not? Current is flowing I1. So this is equals to B1. Clear? So this magnetic field is linked with per turn. This is for per turn because it is establishing everywhere. So this is magnetic field per turn. Now, and the magnetic flux link with the each turn of S2. Now, calculate the amount of magnetic flux there linked with the S2. So, you know, S2, for S2, the magnetic flux link equals to what? B1 into A, right? This is magnetic flux for 1 ton. As the coil 2 having total N2 tons, so the total flux equals to B1 into A into N2, right? So phi is equals to place the value of B1 here. So mu naught N1 I1 upon L. L is the length, small l, multiplied by area A into N2. Clear or not? Now phi 2 is equals to mu naught N1 N2 I1 upon L. Clear? Here it is equals to A. Now, by the formula of mutual induction, by the definition, phi 2 is equals to mi1. Now compare both the right part. So the left part here equals to mi1 and here it is equals to mu naught n1 n2 a upon L, right? So I1 and I1 get cancelled out and m equals to mu naught n1 n2 a upon L. Yes or no? Remember last day the formula of self-induction was mu naught, okay, n1 is square a upon L. Got it? But there is a split of the turns as N1 is in the first coil and N2 in the second coil. So M equals to mu naught N1 N2 A upon L. Clear or not clear? If the core is filled by any magnetic material, so permittivity in the place of air, there will be permittivity of the magnetic material that will be equals to mu. Okay. So equals to mu N1 N2 upon A divided by L. Mu can also be written as mu naught mu R, where mu R is the relative permittivity of the medium. Clear? Okay, so note it down. Okay. So students, you can write like this in the place of mu absolute permittivity of the medium. You can use mu naught into mu R. Clear? One more thing, one more deduction is there. N1 is equals to number of turns per unit length and N2 is equals to, sorry, N2 is small n2 equals to number of turn in the second coil per unit length. Clear? So N1 may be replaced by small n1L and N2 may be replaced by small n2L. Clear or not? So you can place here the value m equals to mu naught mu r. In the place of capital N1, there will be N1L. Here it is N2L into A divided by L. L and L get cancelled out. So your answer equals to mu naught mu r N1 N2 1L 1A. Done. Mu naught mu r N1 N2 N1 here, N2 here, 1L is left as 1 only cancelled out and area A. Clear?